Hey guys, class is in session and you know what that means. Today we will have the second top class and today we're going to talk about something that's really interesting in the context of decentralized networks, and that is consensus mechanisms. Well, as you all know that cryptocurrencies and blockchain networks and sorts are decentralized. That means there's no centralized entities and there are no like central organizations and board of directors and the like who are governing how the protocol pans out in the future. So if that's the case, then well, how does anything ever get done? How does Bitcoin, Ethereum, top and the likes work if there is no central body that's governing it and like shaping it along, as so to speak? Well, to do that, we integrate a mechanism or an algorithm called consensus mechanism. The idea is to integrate a protocol into the underlying network in such a way that a wide area network that's spread all over the world can come to a consensus, or at least the super majority of the network can come to a consensus and decide how the protocol moves forward. It's as simple as that. And while the concept sounds very simplistic on paper, executing it is not easy at all. And not just any algorithm can become a consensus mechanism. For it to happen, it needs to answer a question called the Byzantine generals problem. To understand the Byzantine generals problem, I want you to visualize a castle that's surrounded by an army all over, right? It's surrounded all over. The castle is extremely strong and it's under attack by this particular army. Unfortunately, the army is scattered and the generals in the army can't communicate with each other, right? The only way that this army can conquer the castle is if they attack simultaneously. But they can't communicate with each other effectively because they're decentralized. To do so, the generals send a message through messengers and the messengers convey the message to the generals. And when they receive the message, they attack at once. That's the core idea. However, this system has some very glaring plot holes. Well, what if the messenger is corrupt? What if the messenger does not relay the correct message, and suppose the castle has the king who rules the castle has bribed the messenger and the messenger gives the wrong message as a result? And even if you assume that the messenger is not corrupt, how can we know for sure that the generals themselves are not corrupt? What if two or three generals among the five are corrupt and they decide not to attack, and they just pull out at the last moment, and well, the attack is going to be disaster? This situation is known as the Byzantine generals problem, and this problem is the main issue with any scattered decentralized system which does not have a central governing entity. How do you ensure that your system works cohesively even if there are certain malicious elements present in the network itself? So an algorithm or a consensus mechanism algorithm that works despite having these Byzantine malicious elements present in the system is called a Byzantine fault tolerant consensus mechanism. So your proof of stake, proof of work, all these classic algorithms are all Byzantine fault tolerant, or BFT. Top uses a consensus mechanism that's basically a conjunction of two different algorithms. We have the pBFT, or practical Byzantine fault tolerance, and we have the POS, that is your proof of stake. So why do we need two different consensus mechanisms? Because we want speed along with security. Speed is provided by our modified pBFT, which integrates paralyzation and all that amazing innovations, and POS helps protect us against Sybil attacks. So what we're going to do now is that first we're going to look into how pBFT algorithm works, and then we will see how POS is layered on top of it to create one cohesive consensus mechanism. All right. So as I've already mentioned, pBFT system, or rather pBFT stands for practical Byzantine fault tolerance, and the entire consensus mechanism is divided into 5 phases. We have the request phase, the pre-prepare phase, the prepare phase, the commit phase, and the reply phase. If you look at a white paper, then you will see a diagrammatic description of how this system works. You can find the white paper in the description box below. So let's go through the phases one by one. Let's see what happens here. At first, we have the request phase. The client requests something from our system, right? And in pBFT, we select a random leader from the host of from all the nodes, and each phase has a specific leader attached to it. So the client in the request phase requests certain query from the leader who has been chosen in that time, right? In the pre-prepare phase, the leader sends the query to all the nodes so that they can compute and come up with the appropriate reply, right? From the pre-prepare phase, we have the prepare phase. In the prepare phase, the node works on the particular query, and then they send the result that they think is correct to the leader. And in the commit phase, the leader collects all different queries from all the different nodes and sees which query has the most, which answer rather has the most people agreeing on it. And then in the reply phase, he commits to that answer and gives it back to the client in the reply phase. It's a system phase by phase breakdown of how a query comes into the network, how it gets processed, and how it gets sent back. In our pBFT, we use the same particular mechanism because before we go forward, let's just clarify one thing. In a pBFT system, a particular answer is chosen only if it has 2f plus 1 nodes agreeing on the overall outcome of the system, where f is the total number of faulty nodes in the network. So for example, if we have a very small network with one faulty node, like one malicious nodes, or rather if there are like a network with 6 nodes where one faulty node exists, a total of 2f plus 1, that is 5 other nodes, should agree on a particular query for that query to go through. So that's how the core system of the pBFT works. Now in our pBFT, we have a core strict leader based mechanism. So what we have done is that we have removed the client and the request phase from our system, and we only have the prepare, commit, reply phase. The leader brings in a query that needs to be processed by the rest of the nodes, and the nodes process and bring it back to the leader. We don't have the client asking the leader anything anymore. We just completely eradicate that phase out because we want our system to be as compact and as fast as possible. So as you can imagine, this system puts in a lot of responsibility on the leader. The reason being, since the leader is in charge of all the query and the leader begins the entire query process, so to speak, if the leader is malicious or if the leader is not performing optimally, they can really mess up the entire consensus system, right? So to make sure that there's not too much onus on the authority of the leader, we take 2 steps. First and foremost, if the leader is acting maliciously, the leader node is acting maliciously, we restart the entire protocol, or at least that phase where the leader has been malicious gets restarted. And second thing is that we integrate a VRF algorithm, which is a verifiable random function algorithm, where we randomly keep on choosing leaders from the network itself, so that the choosing of a leader is completely random, and like a malicious node wouldn't know if they're getting selected or not, right? So that is our first spin in the pBFT algorithm. Our second spin lies in parallelizing it, because if you have a function, right, and if you're going to do it sequentially, you're going to have to go through one sequence to another, right? It's not going to be as efficient as it possibly could be. However, if we break down that process into 4 processes and we do the if we execute this process simultaneously, right, in if all the 4 stages are executed simultaneously, that parallelizes the process, making it a lot faster and a lot more efficient. So top uses a parallelized form of the pBFT algorithm. We use 4 techniques of parallelization, which are multi-core and multi-thread parallel computing, multi-role node virtualizations, subgroups within shards, and multiple shards for parallel transactions. We're going to talk about sharding later on, but to have a very basic understanding of what a shard is, imagine that you have a state and you break that state down into fragments. These fragments are called shards. These shards are computed parallelly by the system, and as such it makes the entire thing a lot faster, because if you compute one state sequentially, it's not going to be as efficient. However, if you break it down into smaller components and execute the components simultaneously and parallelly, it's going to make the entire process a lot faster. So that's the pBFT part, or the parallel pBFT part of a consensus algorithm. The next part is proof of stake. So why we integrate proof of stake is because, as amazing as the pBFT is, it's not that secure against Sybil attacks. So to understand a Sybil attack, imagine that I'm a very wealthy person, right? And I own my own node in the network. What if I own several nodes and these malicious nodes act against the entire network and sort of writes over their protocol? So for example, if suppose I'm a multi-zillionaire or something, right, and I own multiple nodes in a particular random cryptocurrency, I take over the entire network because of the 51% attack, and then I can do whatever I please with that entire protocol. pBFT is not secure against this particular attack. Proof of work, the one that Bitcoin, is extremely secure because Bitcoin's proof of work is extremely expensive. Like I said, I have to be a multi-zillionaire or something to actually take over the Bitcoin network. In fact, if I'm not mistaken, the cost of attack for a 51% attack on Bitcoin is around, I think, 2 billion or less than 2 billion. Don't quote me on that, but I think that's the exact figure. So yeah, it is an extremely expensive process. Another consensus mechanism that is pretty resistant against Sybil attacks is proof of stake. Because think about what you have to do to take part in a proof of stake mechanism, right? You have to lock up a certain part of your stake, a certain part of your tokens inside the ecosystem as stake. You can then vote, or you can then choose up the block that enters the blockchain, and you get a block reward that's proportional to your stake. So more your stake, the more your reward. That's the very basic general basic proof of stake mechanism, right? However, if you want to do a Sybil attack, you will need to own 51% of the total tokens that currency has in circulation, and then lock up that stake inside the system itself, and then participate in the proof of stake, and then take over the network. That is also an extremely expensive process, because imagine the amount of money you would need to own more than 51% of a particular thing, right? And on top of that, it might not be feasible to even get your hands on the 51% tokens, because maybe the token owners will not want to give it to you, correct? So that way, proof of stake itself is a Sybil resistant consensus mechanism, which is why we combine the two, pBFT and POS, in a way where all the nodes inside the top system that want to take part in the consensus process will first have to lock up their stake, and then they take part in the highly parallelized efficient pBFT thing. So that way we have speed and then we have security. Now the top twist in its POS algorithm is what we're going to talk about next. So TOP's POS system is not your generic staking mechanism, because if you think about it, any POS algorithm or any currency that uses a POS algorithm, the basic principle that they have is that as long as you have a minimum stake inside the network, you can participate in the consensus mechanism and you can reap the benefits accordingly. However, what if I'm a bad person and I have the money required to have my stake inside the system? Should I benefit more than the other nodes available who may not have the money that I do but are much better people? Well, that's not really fair, is it? So that is why what TOP does is that it uses a system called comprehensive staking mechanism. What comprehensive staking does is that along with the minimum certain amount of deposit that you have to put in to take part in the staking system, you also need to have a good reputation amongst your peers, and you must also have a history of working in the interest of the system. So the three factors that we consider in a comprehensive system are the deposit, that is the amount of money you need to deposit, your credit, as in your history of work, like am I the sort of node that actually does its duties properly, or am I the sort of node that sort of like does things half-heartedly, right? Like I don't consistently take part in the consensus system, I don't conduct the transactions properly, I have a history of malicious behavior, stuff like that. That is part of my reputation score, which gets counted in the comprehensive staking system. Plus the third component is voting. If my peers believe that I am good for the system, then they're going to vote for me, right? They have the capacity of voting for me, and if not, then they won't vote for me, because in TOP we sort of use a liquid democratic system. Either you can take part in the staking yourself, or if you don't want to, you can delegate your tokens to somebody else and let them stake for you. So if I am a good node who's always present 24/7, who's always acting in the interest of the system, people are going to vote for me because they know that I am not going to half-heartedly do my duties, and they will know that they will benefit a lot from the profit sharing and stuff like that, right? So that is the third category we consider in comprehensive staking. So with our modified pBFT and our modified POS algorithm, we combine the two to give you the most innovative and amazing, fast, efficient, secure consensus mechanism in the market today. That is what TOP has running underneath its layers. So I hope you understood what is going on behind the scenes a little bit, because I know that we have to do the sharding and stuff like that. We're going to do that in the future videos, don't worry about it. And if you have any queries, please feel free to ask. We are going to make sure that we get back to you. At the same time, keep your eye out for future TOP videos, and I'm going to do the live white paper reading sessions itself. We did the first live white paper reading and it was a lot of fun. So definitely look forward to more of those, where I'm going to discuss the different terms of the white paper, different sections of the white paper with you. So keep an eye out for the white paper reading sessions and for the TOP videos and the TOP classes. So I hope that this was an amazing learning experience for you, and class dismissed. Bye.